Hopefully. Yeah, well, I use it all the time now.
Yeah.
Okay. You guys ready? Wait. You were born ready. I like it. Okay, so today's topic, not very long. It's called percent yield. The first thing I want to do, though, is point out that percent yield is different than a term we've actually worked on a little bit already called percent difference. Okay. In your labs, I've asked you guys sometimes to calculate a percent difference. And the formula for percent difference is actual minus theoretical divided by theoretical times 100. Or sometimes I use different words. Sometimes I use the words calculated minus expected over expected times 100. Do you guys remember doing this in labs over the last little bit? I hope you do. Ideally, what should your percent difference be? 0. Ideally, when we do a lab, like for example, we did a lab where you were supposed to calculate R. R was supposed to be 8.31. Let's say you got the answer of 12. Were you exactly correct? No. So what we might ask you to do is find out, well, how far off are you? And that's what percent difference does, is it tells you how far off you are. If you get a positive number, it means you were over. If you get a negative number, it means you were below. But ideally, a percent difference should be 0. Okay. Today I'm going to introduce another term. It's called percent yield. Very similar, but there's no subtract theoretical on here. Okay. All you do is actual divided by theoretical times 100. Ideally, for a percent yield, you should get 100%. That would be ideal. Okay. Ideally, when we do a lab, we're going to get a value. For example, we might get 92 grams. But in theory, maybe we should have gotten 97 grams. Did we actually come close to what we were supposed to get? That's not bad. 92 out of 97. Let's say this was your test mark, and I told you you got 92 out of 97. That's pretty good. Okay. Now, in general, in a high school lab, a percent difference of under 10% is pretty good. For a percent yield, it's a little different. We're just not doing the subtract part. Okay. Normally, we would expect to get a certain amount, but in real life, it almost always happens that there are some sorts of errors. And I want to talk about why there could be some errors on this slide right here. I'll come back to the middle slide. Here are some reasons why we might have errors in a lab. Okay. First one is measurement uncertainties. When you guys do a lab and you measure things, if you measure incorrectly, it's going to throw your lab off. For example, we just did a lab where you had to measure temperature. And you were supposed to measure the temperature of a gas, but you weren't able to put the thermometer directly into the gas. So you might have measured water nearby, or room temperature, or you might have looked up the boiling point of that gas, but you probably did not measure properly. Does that make sense? It's not your fault, but pretty much every time you measure something, you could be slightly off. That's a reason why your results might be out. Here's a second reason. Sometimes the chemicals that get used aren't 100% pure. Maybe they're only 98% pure. Cause your results to be off a bit. We haven't done this yet, but we will do in a lab one day. We might get a precipitate. Do you guys remember what a precipitate is? Good. Yeah, it's like a solid. For example, I just did a hypothetical example back here. Which one of these things here would have been the precipitate? Yeah. Now here's the problem. From a practical point of view, it would be a solid inside liquid. How do you get the solid out of a liquid? You could filter it. You could try boiling away the liquid. But chances are what's going to happen is that you're going to lose a little bit of this solid as it gets washed away. As you try to separate the aqueous water from this solid, you may lose a few particles of solid here or there. Does that make sense? So that was this point right here. You may lose some particles when you're trying to weigh your precipitate, your solid stuff. There is a pretty general one right here as well. Maybe we had to make some estimations. For example, we estimated that the pressure in the room was about 91.5 kPas. But what if it wasn't? What if it was actually 92.5 kPas? Does that make sense? Here's another idea. What if a reaction does not complete 100%? What if a reaction only works like, say, 57% of the time? For example, we've already talked about this. Strong acids, like for example HCl, will always break up into H plus and Cl minus, like 100% of the time. You guys remember this from our first unit? But a weak acid, like say let's see, nitric isn't, let's go with H2SO3, that's a weak acid. It will break up into H plus and SO3, but it won't do it 100% of the time. It might do this like, say, 32% of the time. Does that make sense? So most of the time in chem labs, we assume that if a reaction is going to happen, that it always happens. But maybe it doesn't. Maybe only half the time that it works. Maybe only a third of the time it works. That's where those terms strong and weak came from. Strong means it always ionizes and dissociates. Weak means it can, but it may choose not to. It might only do it once in a while. Does that make sense? So, the long story short here is that reactions are not always efficient. Ideally, we would get 100% when we test in our lab. But, I mean, you guys have already seen this. When you guys did labs, I mean, for the most part, did anybody get exactly what you were supposed to? No. Were you close? A couple of groups were actually pretty close. And I know a couple of groups in looking at your labs, you weren't close at all, actually. So be it. I don't want you to lie. I mean, do your math as it's supposed to be. But, I mean, when you do chemistry in a hands-on environment, you will probably rarely, if ever, actually get the number you're expecting. So, long story short, if I ever ask you to find then a percent yield, actual divided by theoretical. So let me do an example, and that's actually all I've got. Let's say we have some copper solid getting produced from aluminum and copper 2 sulfate. So kind of like what I started class with here, I've given you like a word equation. Let's try to write a chemical equation. So what am I reacting? Well, it says copper is being produced. So that means the copper needs to go on the side. Why is it being produced? Well, it looks like aluminum is being reacted with copper 2 sulfate. How do I write copper 2 sulfate? It's actually just CuSO4. Okay, now I've thrown in some states of matter here for aluminum and copper. What's the state of matter for CuSO4 going to be? How do I figure out this guy's state of matter? Where do I look? Copper 2 and sulfate. Solid or aqueous for copper 2 sulfate? Aqueous? Okay. Wait, one more thing though. This is not balanced. It's not even done yet. Because, look, there's aluminum on this side, but there's no aluminum on this side over here. What kind of reaction is taking place? Good, single replacement. So it means that our aluminum will have to go with our sulfate. Have I written this properly though? AlSO4? Aluminum's got a +3, sulfate's got a -2, so you gotta put a 2 and a 3 there. And state of matter, back to the book. See why I touched the first unit before this one? Aluminum and sulfate is also aqueous. Is there a spectator ion in this? I know I didn't ask you for the spectator ion, but is there an ion here that maybe is not all that relevant? Well, here aluminum solid is going to make aluminum aqueous, so I guess that is technically different. Copper aqueous is going to make copper solid. That's actually different. good the SO4 is actually, if I had to write it out, and we're not going to do it, but if you had to write it out, here you have an SO4 that was aqueous, and over here you have an SO4 that was aqueous. It actually, the SO4 was actually not really that relevant. It was a spectator. Well, we're not going to cross it out because I didn't ask you for the net ionic equation, but if I did, we would. One more thing though, this equation is not balanced. So I can't work with it until I balance this thing. So I need a 3 in front of the aluminum. Oh, like this one here? Yeah, I agree. We need a 3 there. We're going to need a 2 and a 3. Does that work? Okay. Okay, so first thing we want to do is figure out what the actual yield was. So based on the information we have here, how much was actually produced? Let me write some stuff here. We started with 3.92 grams of aluminum solid. And we actually produced 6.78 grams of copper. Because like literally it told me right here, this is how much was actually made. How did I, like in a lab setting, how would I have figured out this grams right here? What tool would you need for this? A scale. Yeah, I know, maybe that's a dumb question to ask, but how would we measure this? In the lab, we would measure it on a scale. All right. Now, we got 6.78 grams, but now I'd like to figure out, theoretically, how much should we have got? Should we have gotten more than that, for example? So now let's do theoretical yield, just like we did earlier today. Start with the aluminum, 3.92 grams of aluminum, and let's figure out how much copper we should have got. So, first step, we have grams, we don't want grams, we want moles. So, grams over moles, we need aluminum's molar mass. Okay, so we've canceled out grams. So first step, have to convert it into moles because there is a molar relationship with the recipe. Not a grams relationship, but a molar relationship. So then we now use our recipe for aluminum to copper. And I can cross away the aluminums here. What does the recipe call for? Well, no, I mean right here. What numbers go here? What does this recipe call for here? 3 to 2. Does that make sense? All right. And then last step, you guys are a little ahead of me. Then we need to reconvert it back into grams using a molar mass. Whose molar mass? Copper's. 63.55. So one more time, I gotta rely on you guys for some calculators here. Take 392 aluminum, divide by aluminum's molar mass, times by 3 over 2, times by copper's molar mass. How much copper should we have gotten in theory on paper? Anybody have a number? What'd you get?
13.82 grams.
We only get 3 sig digs, so why don't we just stop at 13.8 grams? Anybody else get 13.8? So this is.
13.9.
What'd you get? 13.8. 8.5? Okay, then 13.9. Well, this is what we theoretically should have gotten based on doing like some calculations on paper. In theory, we should have gotten 13.9 grams. You only got 6.78 grams. Was this a very successful lab? Not really. I mean, you were expecting to get 14 and you got just under 7. So kind of like with like grades and like calculating your percentage, that's what we're going to do now. Let's find your percent yield. You should have gotten 13.9, but instead you got 678.
49.
I get 3 sig digs though, so 48.8. Okay. So let's say this was your conclusion then, and I asked you to conclude, was this a successful lab? 48%?
No.
I mean, you could argue, well, I guess it was.
Under 10.
I mean, if we were to calculate a percent difference, why don't we do that too while we're here? A percent difference would have been 6.78 minus 13.9 divided by 13.9 times 100. Could someone maybe do that one for me real quick? This was the percent difference. This is the percent yield.
5%.
Make sure the top goes in brackets and you calculate it first before you divide by the 13.9. What'd you get?
I don't know what I'm doing wrong.
No, you're right. Negative 51.2%. No, you're right. Okay, so stay with me for like 2 more minutes, guys. I'm almost done. I asked someone to calculate the percent difference. Why is it negative? Because you were below what you were expecting, right? You were really low, and you were below by 51%. Take a look at these two numbers. 48.8, 51.2. How are they related? What do they add to? Yeah. Okay, so here's one way of thinking about it. A percent difference is how far you were like off by. You were off by 51%. Whereas like a percent yield is like your actual percent. Approach this a different way here. Let's say you get 80% on a test. Your percent yield would be 80%. What was your percent difference? Well, if you got 80%, it means you were low by 20%. So really what percent yield does is tell you your percent. Percent difference, though, tells you how off you were. Does that make sense? So these numbers are related. Typically, though, whenever you do a lab, typically you should probably come in low compared to what you should get, because you're always going to lose something. And these are those reasons I gave here again. Usually you're going to have some sort of measurement problems. Whether or not you're measuring, like, say, volume or pressure, like we did earlier, or measuring on a scale, there's always going to be a little error for measuring your numbers incorrectly. Another reason why, in pure chemicals, this is going to be one of the biggest reasons when we eventually do a lab. That was supposed to be a star. That was horrible. There you go. Whenever you have a solid inside of a liquid, you have to filter it out, and you're probably going to lose some of your solids. So it's going to be hard to keep it all. And there's almost always some sort of estimations in a lab. Which again is why when I asked you guys to do your calculations, if you were supposed to get 8.31, nobody actually got 8.31. Does that make sense?
You got close though.
Some groups were close. But I mean, I think one group had like, say, 8.02 out of 8.31.
Yeah, he had like 20 something.
Yeah, so I mean, some groups. So long story short though, just so you guys are aware, if you're off by say about 10% or less in a high school lab, that's usually pretty good. 5% off is usually like fantastic. So, but I mean, don't ever lie about your results in a chem class, at least of mine, in order to get the right answer. I don't want you to like fudge your results. I want you to give me authentic results and then afterwards talk about reasons for why those results weren't as good as they should have been. Which is like why we write conclusions. Any questions? Okay, you guys have 40 minutes left. Where do I want to look here? Here are some things you guys should work on. Okay, it's not due, but I mean, most of you guys, I think when you walked into class today and I asked you to do those first couple of questions, it kind of went a little over your head until I reminded you. You need more practice. Okay. So I would though suggest that the Stoic practice questions that were on the web sheet, this was just like a worksheet. This is probably the best option, but you could do some textbook questions too if you want. But do something over the next half hour to help you learn this a little better, so that next time I ask you a question, you're not like, I forget. I printed a whole bunch off one day and handed them out. I got a few left here. This is what it looks like. But you can just go print another one. I may have more in this file here. I do actually. It's been sitting here for like ever. Sorry, I marked it and I haven't given it back to you.
We found Smart Notebook.
What was that?
We found Smart Notebook.
Oh, perfect.
Yeah,